In this lecture, we are going to model complex reactions in a batch reactor. After this session, you will be able to derive model equations for complex reaction systems and learn how to write model equations for reaction networks in a general and compact way. Let us start with a network of reactions taking place in a batch reactor. In this example, reactant A irreversibly goes to B, which then reacts reversibly to form C and irreversibly to form D. The reaction rate constants for these reactions are indicated on the diagram, and their values are shown below. The reactor starts with a concentration of A of 2 mole per cubic meter. How do we write a mathematical model to describe this system and predict the compositions of all species over time? First, let us see what assumptions can be made. First, in most cases, we can assume perfect mixing in stirred tank reactors. This means that we will take our control volume to be the whole reactor. The second assumption we can make is that the reaction mixture has a constant volume, which simplifies the model a lot. Now we can write the general material balance for the reactor, which you will recall is as follows. The rate of accumulation of material is the sum of all inflows minus the sum of all outflows plus any material that is generated. Here, the material that is generated or consumed is individual species. While the total mass is conserved, the mass or molar amount of individual species can change due to chemical reactions. Applying this to the batch reactor for component A gives the following. The accumulation term is V times the rate of change in the concentration of A with respect to time, since V is constant. What are the units of this term? Mole per second. This is equal to the rate of generation of A, which must also be in mole per second. That is the volume of the mixture multiplied by the reaction rate per unit volume of mixture RA. There are no inflows or outflows because it is a batch reactor. We don't worry about the details of filling and emptying the reactor, especially if the reaction time is large compared to the filling and emptying times. Note that RA is defined as the rate of generation of A per unit volume of mixture. Its units must be mole per m cube per second. For a first order reaction, you usually write negative RA equal to K1CA, since A is being consumed by the reaction. Now we can substitute the reaction rate expression into the material balance and cancel the volume. This leaves the following ordinary differential equation. Okay, so to recap, we can write the material balance for component A as follows. Okay, so the accumulation term is equal to the inflows minus outflows plus the generation term. For a batch reactor, we can drop the inflow and outflow terms. The accumulation term is the rate of change in the number of moles of A with respect to time. And we can write that out as the derivative with respect to time of volume times the concentration. Volume times the concentration will give you the number of moles. And this is equal to the rate of generation of A. So this is per unit volume. So we have to multiply this by the volume V. So that each term has the units of mole per second. Okay, so again, RA has the units of mole per m cubed per second. Okay, so we defined RA as the rate of generation, but in our example, A is being consumed. So we can write the rate of the consumption of A, so note the negative sign. This is equal to, if we assume first order reaction, this is K1 CA. So here we can take the volume out of the derivative because we assume that the volume is constant. dt. And for the right-hand side, we can substitute this expression for RA. This will become V K1 CA. And we can cancel the V. So we'll end up with dCA dt equal to negative K1 CA. And this describes the rate of concentration of A with respect to time. Okay, so for the other components, B, C, and D, we can write their material balances in the same manner. So we can generalize using an index I to represent the elements of the set containing components A, B, C, and D. We can say that the rate of change in the concentration of each component with respect to time, this is equal to the rate of generation of component I per unit volume of the reactor. And this is true for all I in the elements of the sets containing A, B, C, and D. As I've said, we can write the material balance for the other components in exactly the same way. Each one states that the rate of change of the concentration is equal to the rate of generation per unit volume of mixture. Then we just have to define Ri for each component. First, let's write the rate of generation of B. Looking at the reaction mechanism, you can see that B is produced by reactions 1 and 3, whereas it is consumed by reactions 2 and 4. Assuming all reactions are first order, that gives RB as, okay, so by the first reaction, B is produced, so we can write K1, the rate constant of the first reaction, times the concentration of A. Okay, so by the second reaction, B is consumed. So we write negative K2 times the concentration of B. By the third reaction, B is produced. So we write positive K3 times the concentration of C. And then finally, by the fourth reaction, B is consumed. So we write negative K4 times the concentration of B. So we can use the same approach to write the rate of generation of C. So C is produced by reaction 2 and consumed by reaction 3. Therefore, RC is equal to, okay, so by the second reaction, B is produced. So we can write positive K2 times the concentration of B. And then by the third reaction, C is consumed. So we write minus K3 times the concentration of C. And then finally, RD, the rate of generation of D. So D is only produced by reaction 4. So we can write, okay, so positive K4 times the concentration of B. Now we can write all material balances, one for each component in the system. But before we complete the model, have a think about what the equations would be if we had 2A goes to B instead of the equimolar first reaction. So what if this is 2A goes to B instead of A goes to B? The last thing we need to complete our model is the initial condition for each component. It is a system of 4 ODEs, so we therefore need 4 initial conditions before we can solve it. The full model with initial conditions is therefore as shown on the slide. For our example, Ca0 is given as 2 moles per m cube, and Cb0, Cz0, and Cd0 are all 0, meaning that at the start of the reaction, there's only reactant A, and there are no intermediates or products produced yet. So let's go back to the question of what happens if the first reaction is 2A goes to B. Did you get it? I will teach you another method using the reaction rates to get the rate of generation of each component, and then writing the material balance from there. So this is our reaction network where we have 4 reactions, and all reactions are first order. So the first reaction is 2A goes to B with the rate constant K1. The second reaction is B goes to C with the rate constant K2. Third reaction is C goes to B with rate constant K3. And the fourth reaction is B goes to D with rate constant K4. So we can write the rate of reaction 1 as, okay, R1. This is equal to the rate constant, okay, times Ca. Okay, this is because all reactions are first order. Okay, and then the rate of reaction 2, B goes to C here. Okay, so rate of reaction 2, this is equal to K2 times Cb. Okay, and the rate of reaction 3, okay, is K3 times the concentration of C. And the rate of reaction 4 is equal to K4 times the concentration of B. Okay? So when I say reaction rates, what I mean is how fast each reaction is going. And that is different from the rate of generation of a component. Okay? But we can derive the rate of generation of a component using the reaction rates. Okay, so how do we do that? Okay, so let's consider component A first. Okay, so for component A, so we would like the rate of generation of A. And in the reaction, we can see that A is only involved in reaction 1. Okay, so 2A goes to B. And every time reaction 1 takes place, 2A gets consumed. Okay, so every time reaction 1 takes place, 2A gets consumed. So therefore, rate of generation by reaction 1, so I can write that as, okay, so rate of reaction 1 is K1 Ca, and every time that takes place, 2A gets consumed. So I need to multiply this, the rate of reaction 1, with negative 2. Okay? And that's it, because A is only involved in reaction 1. Okay, so let's do it for component B. Okay, so rate of generation of component B. Okay, so from the reaction, we can see that component B is involved in 4 reactions. Okay, so in reaction 1, reaction 2, okay, so in reaction 1, B is produced. In reaction 2, B is consumed. In reaction 3, B is produced. And in reaction 4, B is consumed. Okay, so by the reaction 1, okay, so every time reaction 1 takes place, 1B is generated. Okay, so from reaction 1, the rate of reaction 1 is K1 Ca, and every time that takes place, I get 1B. Okay, so I multiply this by 1. Okay, so I'll just leave it like that because it's multiplied by 1. Okay, so that's from reaction 1. Okay, what about contribution from reaction 2? So B goes to C. So every time reaction 2 takes place, 1B is consumed. Okay, so reaction 2, rate of reaction 2 is given by this. So K2CB, and every time that takes place, 1B gets consumed. So therefore, the contribution from reaction 2 is negative K2CB. Okay, so contribution from reaction 3. So every time reaction 3 takes place, 1B is produced. So therefore, that's plus. Okay, and then rate of reaction 3 is K3 C. And then finally, contribution from reaction 4. So every time reaction 4 takes place, 1B gets consumed. So that means negative 1 times the rate of reaction 4. Okay, so that's the rate of generation of B. Okay, so let's also write the rate of generation of component C. C is involved in reactions 2 and 3. So the rate of generation of component C from reaction 2 is, okay, so the rate of reaction 2, that's K2CB. And every time reaction 2 takes place, I get 1C. So multiply this by 1. And then contribution from reaction 3. So every time this takes place, 1C is consumed. So minus rate, so minus 1 times the rate of reaction 3. So K3 C C. Okay, and then finally, rate of generation of component D. Okay, so that's RD, and D is on the is involved only in one reaction, and that's reaction 4. Okay, and every time reaction 4 takes place, 1D is produced. So I can just write, okay, so rate of reaction 4, K4 CB, and then multiply that by 1. Okay, so now we have all of the rates of generation of all of the components. So from the mass balance, for a batch reactor, we know that the change of concentration of a component I with respect to time, that is just equal to the rate of generation of that component. Okay, so you can write this for all I in the set containing the elements A, B, and so on. Okay, so this is our model, and you will just have to expand it and substitute the rates of generation. Okay, so Ri, so write it for each component. So A, B, C, and D. We have the rates here. So rate of generation of A, rates of generation of B, C, and D. Let us expand this equation for component A. Okay, so we can write, so for component A, that's just dCA dt equal to Ra. Okay, and Ra is equal to this one. Okay, so we derived this earlier, negative 2 K1Ca. Negative 2 K1 Ca. Okay, let's do that for component B. So dCB dt is equal to Rb, and Rb is equal to this, okay, which we derived earlier. That's K1 Okay, I will let you do components C and D. Okay, so putting it all together, this is our model for the alternative reaction mechanism where 2A goes to B. As you can see, this is the same as the model from the last example, except for the negative 2 here. I have another example here, and I would like you to try it on your own. Okay, so derive a model that describes the rate of change in the concentration of each of the substances involved in the following reaction network. Okay, so all reactions are first order. Pause the video now and try it. Okay, so what answer did you get? Okay, so we are given 4 reactions, all first order. So we can write the rate of reaction 1. Okay, so that's equal to K1 Ca. Rate of reaction 2 is equal to K2 Cb. Okay, and rate of reaction 3 is equal to K3 Cc. Rate of reaction 4 is equal to K4 Cb. Okay, so we can write the rate of generation of A. Okay, so A is only involved in the first reaction. So the rate of the first reaction is K1Ca. And every time this takes place, 2A is consumed. So minus 2 K1Ca. Okay, so rate of generation of B. Okay, so B is involved in all four reactions. Okay, so the contribution from the first reaction is K1 Ca, and I have to multiply it by 3. Okay, because every time reaction 1 takes place, I get 3B. The contribution from reaction 2 is, okay, so minus 3 K2 Cb. Contribution from reaction 3 is plus 3, okay, so K3 Cc. And contribution from reaction 4 is minus 3 K4 Cb. Okay, so rate of generation of C is equal to, okay, so C is involved in two reactions, reactions 2 and 3. So from reaction 2, okay, so that's positive 4 times the rate of reaction 2, so K2 Cb. Contribution from reaction 3 is minus 4 K3 Cc. Okay, and then finally, rate of generation of component D. So component D is only involved in one reaction, and that's reaction 4. So 5D is produced every time reaction 4 takes place. K4 Cb. Okay. So for a batch reactor, the change in concentration of component I with respect to time is equal to the rate of generation of component I. Okay, and you can write this for all I in the set containing components A, B, and so on. Okay, so you just have to expand this. Okay, expand this for every component A, B, C, and D, and substitute the expression for the rates of generation of each component I. Okay, so it's easy to formulate the model for small reaction network. Say we have 4 to 10 reactions. However, some systems can have a large number of equations. Sometimes there are hundreds or thousands of individual reactions. So let's generalize it and write the model in compact form. Okay, so reaction network model. And we'll write it in compact form. Okay, so we will represent the species or components by an index I. So I, okay, so that will represent the species or components. Okay, so that is, okay, the elements of the set containing your components A, B, and so on. And we will use the index J, okay, to represent the reactions. Okay, so that can be reaction 1, reaction 2, and so on. So using the index notation, we can write the rate of reaction J. Okay, so rate of reaction J. So that's just equal to the rate constant of reaction J. Okay, and we need to take the product, okay, of the concentration of I. Okay, so we want this model to be general. So in our previous examples, we considered that all of the reactions are first order. Okay, but we want this to be general, so we will consider all of the cases, including the reactions with order greater than 1. Okay, so if that's the case, so this is Ci and raised to omega ij. Okay, so omega ij, that is the order of reaction J with respect to component I. Okay, and this product is over all component I. Okay, therefore, the rate of change in concentration of component I with respect to time can be written as the summation, okay, all over the reaction J. Okay, and we will use this parameter. So this is nu. Okay, so this is the stoichiometric coefficient of component I in reaction J. Okay, multiply by the rate of reaction J. Okay, and you can write this equation for all I in the elements or in the sets containing the components A, B, and so on. Okay, so again, this parameter here, so nu ij, so that is your stoichiometric coefficient. Okay, stoichiometric coefficient of component I in reaction J. Okay, so I have another exercise for you. So here is another reaction network. So there are 4 reactions. Reactions 1 and 3 are first order, and reactions 2 and 4 are second order. So I would like you to apply the reaction network model in compact form to derive the model describing the rates of change and concentration of the components. Okay, so pause the video now. So how did you do? Were you able to derive the differential equations? Okay, so this is our reaction network comprising 4 reactions. Okay, so reactions 1 and 3 are first order. Okay, so I have indicated that here in our diagram with a red ink. So reactions 1 and 2, first order, while reactions 2 and 4 are second order. So we are asked to write the reaction network model in compact form. Okay, so we need to identify So first we need to identify the species or components as well as the reactions. Okay, so I represents species or components. Okay, so in the set A, B, C, and D. And then J represents the reactions. Okay, so in our case, so we have a set of reactions containing reaction 1, reaction 2, reaction 3, and reaction 4. Okay, so the next thing to do is to construct our stoichiometric coefficient matrix and the reaction order matrix. Okay, so I need to construct the new IJ matrix and the reaction order matrix. Okay, so this is the stoichiometric coefficient matrix, and this one is the reaction order matrix. Okay, so let's start first with our stoichiometric coefficient matrix. Okay, so new for component 1, reaction 1. Okay, so what's the stoichiometric coefficient for the first component and first reaction? So first component 1 is A and reaction 1 is reaction 1. So I will have a look at reaction 1 and look at the stoichiometric coefficient for A. Okay, and in this reaction, A is being consumed. So the stoichiometric coefficient is -2. Okay, so the next one, so stoichiometric coefficient of component 2 in reaction 1. Okay, so reaction 1, stoichiometric coefficient of component 2, so that's B. So here, that is 3. So it is a product, B is a product, so it's +3. And then stoichiometric coefficient of component 3 in reaction 1. Okay, so component 3 is C. I still have to look at reaction 1. C is not involved in this reaction, so it's 0. And then new, okay, stoichiometric coefficient for component 4 in reaction 1. Component 4 is D, but D is not involved in reaction 1. So this is 0. Okay, the next one, I will do the same thing for reaction 2. Okay, so for reaction 2, so the first one is the stoichiometric coefficient of component 1 in reaction 2. So component 1 is A, and I need to have a look at reaction 2. So A is not involved in reaction 2, so this is 0. Stoichiometric coefficient of component 2 in reaction 2. Component 2 is B, and it is a reactant in reaction 2. So this is -3. Okay, negative because it is being consumed. Then I will do the same thing for component 3 and reaction 2. So component 3 is C, reactant C. Have a look at reaction 2. C is being produced, so it's positive for here. And okay, for component 4 in reaction 2, component 4 is D, but D is not involved in this reaction, so that's 0. Okay, so for component 1 in reaction 3, so have a look at reaction 3. Component 1 is A. A is not involved, so that's 0. Component 2 in reaction 3. component 2 is B, and B is produced. So that's positive 3. Component 3 in reaction 3. So C is being consumed in reaction 3. So right here, negative 4. And then stoichiometric coefficient of component 4 in reaction D. D is not involved in reaction 3. So this is 0. And then finally, okay, for the last column, so stoichiometric coefficient of component 1 in reaction 4. Okay, so A is not involved in reaction 4, so this is 0. Component 2 in reaction 4, B is being consumed in reaction 4, so that's minus 3 here. And then component 3 in reaction 4, so component 3 is C, but it is not involved in reaction 4, so that's 0. And then finally, stoichiometric coefficient for component 4 in reaction 4. So component D is our component 4, and in reaction 4, it is being produced. So it's positive 5. Okay, so I hope you got all of the stoichiometric coefficients correctly. So we can write that in matrix format. So nu of ij. Okay, so first column would be this. 0, 0. Next column is 3, 4, and 0. 0, 3, negative 4, 0. So 0, negative 3, 0, and 5. Okay? So what about our reaction order matrix? So Wij. So we know that it's going to be a 4 by 4 matrix as well. Okay, so what is the order of the first reaction with respect to component A? Okay, so first reaction, the order of the first reaction with respect to component A is 1. So I'll write 1 here. Okay, so still looking at the first reaction. Okay, so what is the order of this reaction with respect to component 2, which is B? Okay, so it's 0. So when we look at the reaction order, when we write the reaction order, it is only for the reactant. Okay, we consider explicitly the reversed reaction. So for example, in this one, in the reversible reaction, so in this reaction here, so for reaction 2, so it is second order with respect to B. Okay, but here we are working on this column, on the first column. So order of reaction 1 with respect to B is 0. Okay, and then order of reaction 1 with respect to component 3, so that's C, so this is 0. And the order of reaction 1 with respect to component 4 is D. Okay, so this is 0. Okay, so that's the first column of our reaction order matrix. Okay, let's work on the next column. So the next column, so that's reaction 2. Okay, so let's look at reaction 2. So what is the order with respect to component 1? Component 1 is component A. Okay, so it doesn't depend on A. A is not in this reaction, so this is 0. Okay, so what is the order of reaction 2 with respect to B? So with respect to B, so it says here that it's second order with respect to B. So we put 2 here. Okay, what is the order with respect to component C? So that's 0. And order with respect to D, so that is 0. Okay. So for the third column, so third column is for the third reaction. Okay, but we already know, okay, that for the third reaction, it is first order with respect to component C. Okay, component C is the third component. So I'll just put 1 here, okay, in the third row. Okay, because I know that reaction 3 is first order with respect to C. And then it doesn't depend. So the rate of reaction 3 doesn't depend on other components. So this will be 0, this will be 0, and this will be 0. Okay, and then for the fourth column, so this is for the fourth reaction. So I know that this reaction is second order with respect to B. So second order with respect to B. So the second row is for B. So I'll put 2 here. And this reaction doesn't depend on the concentration of any other elements or any other components. So this will be 0, this will be 0, and this will be 0. Okay, and this is our reaction order matrix. So I hope you got this correctly as well. Okay, so now that we have our stoichiometric coefficient and reactor order matrix, we are now ready to write the reaction rates, okay, for each reaction. So that's Rj, so reaction rate of reaction J. Okay, so that is equal to Kj product over I, okay, of the concentration I raised to the order. Okay, so reaction order with respect to I, or order of reaction J with respect to component I. Okay, so let's do this. Okay, so let's expand this for every reaction. Okay, so this one you can write it for every reaction in J. Okay, so reaction 1, reaction 2, reaction 3, and reaction 4. Okay, so let's start with reaction 1. So J is equal to 1. So that will be R1. This is equal to, okay, so K1. Okay, so now we will have to look at our matrix. Okay, our reaction order matrix. So this one, we want J equal to 1. Okay, so J is our reaction, the index for reaction. So we will just have to look at this column here. Okay, so this is the column that we need for J is equal to 1. Okay, so I'll put it in the box. Okay, so for J is equal to 1, so for component A, so CA, the order is 1. Okay, so the next row, so that's CB, the order is 0. Okay, so the next row, so CC, that is 0. And then for CD, that is 0. Okay, so therefore, R1 is K1 CA. Okay, because anything raised to 0 is just 1. Okay, so this will simplify to this. Okay, so let's do the same thing for reaction 2. Okay, so for reaction 2, what we need is this column. Okay, reaction 2. So we just write R2 is equal to K2. Yeah, I'm just expanding this formula here. So product of the concentration raised to the order. So the first component is Ca, that's raised to 0. And then second component is Cb, and that's second order here. Okay, 2. And then Cc raised to 0, Cd raised to 0. So this guy will simplify to K2 Cb squared. Okay, so I can also do the same thing for reaction 3. So for reaction 3, I just need to look at the third column, and everything is 0 apart from the one for component 3. Component 3 is C. Okay, so this one I can just write. So Kj, so this is K3, and on the component 3 has a non-zero order. So I just write here C, C, and it's first order, so Cc raised to 1. And then finally, for reaction 4, okay, so we have R4, and then I need to take a look at the fourth column of our reaction order matrix. And everything is 0 apart from the 1 for component 2 or component B. So I can just write here K4, component 2 is component B, CB squared. Okay, so those are our reaction rates. Okay, so now we are ready to write the differential equation. So for a batch reactor, we know that the rate of change in concentration of component I with respect to time, it's equal to the summation over J of the stoichiometric coefficient multiplied by the rate of reaction. So this is for every I in the set containing A, B, C, and D. Okay, so let's expand this equation for each component. Okay, so now I will need to have a look at my stoichiometric coefficient matrix. Okay, so for component A, so I is equal to A. So dCA dt, that is equal to, okay, so V A and first reaction, so V11, so that's -2. Okay, times, so I'm doing it for J equal to 1, so R1. Okay, and it's a summation, so for the next reaction, contribution from reaction 2, so this is the contribution from reaction 1. So for this one, so I will have to look at, because I'm writing it for every component I. Okay, so I will have to look at every row. So each row of this matrix is for a component I. Okay, and this is for component A. So -2R1, and then the next one, so Vij, so contribution from reaction 2, so that's 0. Okay, so Vij, so V1, 2 is 0 times R2. Okay, and then from the third reaction, so V13, so that's this one, so that's 0, R3, plus, okay, so contribution from the fourth reaction, stoichiometric coefficient is 0, R4. Okay, so this is just equal to -2 R1, but we already have R1 previously, so I'll just substitute that here. So 2, okay, R1, so K1 CA. So this one, which we derived previously for R1. Okay, so let's do the same thing for component B. So dCB dt. Okay, so this time we'll have to look at the row for component B. So that is the next row here. Okay, this row here. Okay, so contribution from reaction 1 is 3. Okay, so 3, so this is the coefficient here is 3, and this is R1 plus, okay, so from reaction 2, so that's minus, okay, so let's just put minus here. So this is 3, okay, R2 plus, okay, so from the third reaction, so that's 3, my coefficient, okay, so this is nu 2, 3, okay, and nu 2, 3 is this one here. So 3 times R3, and then from the fourth reaction, the contribution is, so again, it's minus there. So this is -3 R4. Okay, and then we just substitute the values or the expression for the rate constants, which we already have previously. Okay, so we'll just have to write 3 R1. R1 is K1 CA minus 3. Okay, so R2 is K2 CB squared plus 3 R3. R3 is K3 CC minus 3R4 is K4, 3K4 CV squared. Okay. I is equal to C. So that's D, CC, DT. Okay, so let's look at our coefficients for component C. So stoichiometric coefficient is the third column. So it's 0 for the first reaction, plus 4 for the second reaction, minus 4 for the third reaction, and 0 for the fourth reaction. Okay, so this one, so that's 0. So this is just 4R2 K2 CB squared minus 4R3, which is K3 CC. And then finally, for component D, so we have D CD over dt. Okay, so stoichiometric coefficient for component D is the final row, and we only have one non-zero element, and that is for reaction 4. So we just write 5R4, and this is 5. So R4 is K4 CB squared. Okay, so these are the differential equations that describe the rate of change in concentration of each component. So to complete our model, we need to indicate the initial conditions. Okay, so these are all with respect to time. So in order to solve this, we need initial conditions. Okay, so at time equal to 0, so I'll put it on this side because I don't have space on the right-hand side. Okay, but normally you would put it on the right. Okay, so CA, 0, so time t0, so I'll just indicate it as CA subscript 0. So any number could be 0 or non-zero, but this is reactant A. So in our reaction, A is a reactant, so most likely this will be non-zero. And then same thing for B. So concentration would be at time 0. Just put CV0 and CC0. This is C. Some number, this is 0. And then CD 0. Okay. So again, typically this would be non-zero. And for initial concentrations of B, C, and D, they could be they can be 0 or non-zero. So it depends on the system. Okay, so this is our model. Okay. So if I ask you to write it in expanded form, so you'll have to give me this one. But if I asked you to write it in compact form, what you can give me is just the coefficients, stoichiometric coefficient, so matrices, so the matrix for stoichiometric coefficient and the matrix for the reaction order. And you have to define RJ, so just write this equation here and write this equation here. Okay, so again, if I ask you to give me the model in compact form, I would expect you to give me the matrices for the stoichiometric coefficient and reaction order, as well as the formula or the equation for reaction rate and the change in concentration with respect to time. But if I ask you to write it in expanded form, I expect to see this. Okay, I expect to see each differential equation for each component. Okay, so for both cases, you will have to present the initial conditions as well. So going back to the example in the slide, we can also write this model in compact form, which I have done here. So here are the matrices for the stoichiometric coefficients and reaction order. So from these, we can write the expressions for the reaction rates and the differential equations describing the rate of change in concentration of each component. So here are all of the things. These are all of the things that you need to present when you are asked to write the model in compact form. You need to present the differential equation and reaction rates in index notation, along with the matrices for the stoichiometric coefficients and reaction order. And do not forget to include the initial conditions. The compact form is very useful because it saves you having to write out every balance equation individually. So it's much quicker, neater, and there's less chance of making mistakes. It also makes your models more general. You don't have to set up a new model for a batch reactor each time you change your set of reactions. You have just these two indexed equations set up, and all you need to do is to change the reactions to redefine the stoichiometric and order matrices. That is, you set the number of components, the number of reactions, and then specify the values of all elements in the matrices. You never have to change the actual equations. This type of model for reaction systems has many industrial applications. Some examples are polymerization reactions, Fischer-Tropsch synthesis, and biological systems. These systems can have hundreds or even thousands of chemical species and reactions, so doing the balances one by one is not practical. So here is a problem that I would like you to do on your own time. We have a reaction network shown in the middle involving components A through to R with 18 reactions. So derive a model using the compact notation or in compact form that describes the rate of change in concentration of each of the species for this network. So once you have done it, please take a photo of your solution and post it on our Padlet board. So this network is inspired by the simplified diagram of the amino acid synthesis pathway shown on the right. I have added the stoichiometric coefficients to make things a bit more interesting. Reaction networks like these, which aim to describe the behavior of an entire living cell, can have hundreds or even thousands of reactions. So you can read more about this reaction network by clicking on the link. To summarize, in this session, we looked at how to derive a model for a batch reactor with a complex set of reactions. We had to write down the rate of generation of each species carefully, looking at the reaction mechanism. This led to 4 distinct differential equations, and we also defined the initial conditions. When you have systems with many more species and reactions, this can be cumbersome and could lead to errors when you write your simulation in MATLAB or other software. A more compact approach is to define rates of each reaction using reaction orders. Then the rates of generation of each species come from the reaction rates and the stoichiometric coefficient matrix. In our case, for different ODEs can be written as a single indexed equation, and we need one indexed equation to define the reaction rates. Okay, so lastly, I would like to remind you that the problem sheet for the MATLAB simulations session 2 is now available on Moodle. So please download and have a go at answering the questions now.